Okay, so it's my pleasure to introduce Sam Grushevsky, and he's going to talk about degenerations of Riemann surfaces and meromorphic one-forms on them.
Looks like degenerations of degenerations.
We'll see.
Degenerates, I know. I think this is my post-sabbatical talk delayed by pleasant duties for some months. What I'm going to talk about, there are two series of works with one set of collaborators and another set of collaborators. You can read a couple of papers from the archive. You can read a few more files from my computer, but not yet. And I gave, especially for this group of papers, there are 5 of us, and all of us gave many talks. Mostly these were tight Euler dynamics conferences, and I don't think many of you were present at any of them. My New Year's resolution was actually not to talk about this anymore because I got so sick and tired of talking about it, but I'm sort of breaking it, which also means I have changed the talk somewhat. And my goal will be to describe the kind of questions we're trying to address without necessarily saying all the details of what we can get. And I'd like to first explain to you what questions we study, and then only towards the end we'll probably have something of results. I mean, I'll indicate the kind of language in which to expect results. I'm very much honored by the overflow. Yes, you should steal my share, but it only solves part of it. So this will be about the degenerations of Riemann surfaces. When I say Riemann surface, for me it's always a compact Riemann surface. I wrote Riemann surfaces in the title of the talk, hoping it sounds less scary, but I really mean complex algebraic curves. And a Riemann surface will always be denoted x in this talk. There will be no other x's. And it will always have a genome G. And I will talk about degenerations of Riemann surfaces and meromorphic one-forms, which will be denoted omega on them. And I wanted to first tell you two setups, two kinds of probably two interesting setups. And I'll tell you what these are, and then I'll try to tell you why you may care about certain degenerations. So setup number 1 comes from type Euler dynamics. So I take x, and I take omega, and I take a point, Zx, where omega does not have a zero pole. Recall that for me, one point will be meromorphic. In fact, it's something about which only holomorphic for the purposes of this presentation, but meromorphic. So this means locally, I can write omega as dx, where x is a local holomorphic coordinate on x near the point z. Okay? So the points on Riemann surfaces will always be denoted z. I will get confused if I don't do that. If I do that, then I have an SO2R action on x, because x is an R2, and of course SO2R sends R2 to R2. So it sends x to some other x prime. And I can then think that it actually acts on omega by sending it to dx prime. Okay? This is a formula for an action. I use C as R2, SO2Rx. The coordinate changes, D of the coordinate also changes. This is a no longer holomorphic one form on X, but in fact,
No longer meromorphic.
meromorphic. I mean, it has no complex differentiability, but locally at this point where I'm working, it's holomorphic anyway. This is all local so far. But in fact, there exists, and in fact unique, complex structure x prime on the same topological Riemann surface, such that omega prime is holomorphic on x prime. This is a non-trivial statement. It's easy to prove. I won't prove it. You can draw local pictures and local charts, These are called flat surfaces because you're sort of talking about flat structures with cone angles. So what this says is at every point I choose an arbitrary, so I choose an arbitrary global meromorphic form. Locally at every point I write it as dx, then I act on x by SL2R. That changes the form locally, but globally they glue to a global meromorphic, to a global form.
So you do this at every point,
I do this at every point.
simultaneously.
Simultaneously, and then you have to worry what happens at zeros and poles, because I haven't told you anything about what happens at zeros and
Use the
poles.
same element in SL2R.
With the same element, gamma.
The key thing, it's not a local, it's not an arbitrary local homomorphic coordinate. It comes from a given fixed
So then
form.
this, I start with x omega, and I end up with x prime omega prime. So what I'm trying to say is that there is an SL2R action which sends x omega to x prime omega prime. And what it does is at every point of x, which is not a zero or a pole of omega, I do that with a given element of SL2R, and then I have to argue that it goes on correctly at zeros and poles. And one thing I want to point out, this action preserves the zeros and poles of omega with multiplicity. Okay. I didn't tell you what the action does, so I just say do something around, and then you need to argue that it works out correctly locally. Of course, near a zero pole, you should write omega as x to some power dx and try to think that you act in the same way, and this will be correct. And then you have to argue that it patches together, which I will not argue. But it can be argued, it's very easy, but not for a colloquium.
Can you understand this action simply that omega goes to some linear combination of omega and omega complex conjugate?
No, absolutely not. It's not.
So then I understand what this action is.
There is no section.
Action.
So the action is the following. I take a Riemann surface, I take a holomorphic one form on it, I forget that this was a complex Riemann surface. Now, at each point of a Riemann, z of a Riemann surface, I write omega as dx, where x is a local coordinate.
X is just an integral of
X is locally an integral of omega, away from zeros poles, otherwise it's on roots here. And then I act on this integral. X is a complex number. It's an element in R2.
But
So
what, Nikita, what he said is correct, though. The new thing is a combination
I'll
of.
finish his explanation.
So first of all, what he said is wrong. Second, I think I know it's wrong. And third, I'm trying to explain myself. So let me do that. Omega is not a linear, omega prime is not a linear combination of omega and omega bar because it lives on a different Riemann surface for one. So I don't even know what it means. It has no such holomorphistic property. Locally, I have taken omega. Omega is locally dx. I act on x linearly.
Yes.
I get a new coordinate x prime. I think the
Which is a linear combination of the
So
old x and x
locally,
bar,
omega
and when you differentiate it, it's.
Locally, it's true. Globally, no. Globally, I don't know what it is.
So if I can write locally, omega prime is equal to a omega plus b omega bar, and a and b are the same for each chart, then can't I write globally as a
No, I mean,
it's a simple form? I don't care about
They're
the
not the same.
They're not the same for all charts. And then you really need to worry about poles. You should not think like that. I mean, I can make what you said in a correct statement by cutting this up correctly and saying something like that. That has not been used for anything particularly good that I know. So you should not think like that. It's a linear action of SL2R.
And it's not happening on the universal cover.
There is no universal cover.
You could
No,
in principle look and it's
I
not
say
that.
complex Riemann surface. I was not going to talk about this. I just wanted to impress upon you that despite the fact, no, I mean, I wanted to, so the point of that was to say that what you have is an action on the following things. A pair consisting of a Riemann surface and a meromorphic dynamics, people like holomorphic because you can have area 1, never mind, forms. SL2R acts on this, and you can study the dynamical properties of this action, and then in here I'm supposed to write the list of field medals awarded for studying this action, and it's a long list, okay? Which I won't do because it's embarrassing and we don't know what to draw up this. But this is an interesting action, and it preserves multiplicities of zeros and poles of a form omega. So if I have omega which has 3 zeros with multiplicity 5, omega prime will have 3 zeros with multiplicity 5 as well. So this is a motivation for trying to understand the geometry of pairs consisting of a Riemann surface together with a meromorphic one form with prescribed multiplicities of zeros and poles.
Do you know who first studied this action or introduced it?
This is, I mean, I could write beach in very big letters somewhere around here, but he's not the first. I mean, Mazur should be written, Howard Mazur, Howard should be written.
So every time you say something and you're not going to talk about it, then you can get the question.
I'm aware of that. No, I won't. No, I don't want to talk
I
about
wanted
it.
to say beach because he happened to die this year.
Yes,
so
I'm
this is
aware
a
of
major
that.
thing.
Yeah. It goes back further, but people did not focus on dynamics as much until this occurs. Okay? I did want to talk about this because it's a very natural context where there is something, some action that is very interesting dynamically, which I will not talk about. It preserves multiplicities of zeros and poles of omega. And this is one setup in which I want to work. I want to work with pairs consisting of a Riemann surface together with a meromorphic one form with prescribed set of zeros and poles. I will ignore the action.
You mean the numbers is prescribed?
The set of multiplicities is prescribed.
Okay.
Because I cannot identify x and x prime in any meaningful way. They're different complex Riemann surfaces.
Yeah, but they have periods, right? So I mean, is the action on the periods just that you use the coefficients from SL2R?
It's more complicated. I mean, when you say period, you
I mean,
want
on
to do
punctuated
it will start going through zeros. It's not.
Yeah,
it's
you have to punctuate it.
Yeah, but then when you punctuate, you've created new periods that you don't know where they went. So the action is not so easy. When you're saying the word period, you're also choosing the basis for H1, which you cannot do globally, you can do locally. So there is a period foliation called rel foliation dynamics, which is equiperiodic foliation locally. That plays a role in this study, but there are pitfalls that need to be avoided. But I want to develop techniques that would apply to this. I don't want to study SL2R action here because doing anything dynamical here I would be embarrassed. Okay, saying the word technical here, I'm less embarrassed. So that's one setup. So that was one. The second setup of a very different nature is the following. So suppose X is a curve of degree D. So if I write down a random equation of homogeneous and three coordinates of degree D, I will get a curve. It doesn't have to be smooth. So you can ask what kind of singularities it has, and suppose the only singularities I have are nodes. So by a node, I mean something that locally looks like xy is equal to 0 in C2, which is equivalent to saying x squared is equal to y squared in C2, locally near the origin, and simple cusps. So this means locally, there's an x squared is equal to y cubed. Why only these two kinds? Well, one reason is this is the two simplest kinds of singularities. I'll tell you another reason in a few minutes. Okay? So suppose you have such a curve. Question: what are possible numbers of cusps? On curves of degree D. Okay? So this is a singular curve, which is given by one equation of degree D, and I want to know what are the possible numbers of cusps. And this problem has long history. You can get bounds, so maximum number of cusps that you can possibly have is the only thing people studied. People didn't study whether every number of cusps is possible. It's a separate story. So the maximum number of cusps is easy to check is less than, well, d squared over 2 plus O of d, just because the genus you can compute and each cusp picks up one genus. And you can also argue that's at least d squared over 4 plus O of d, and this is work of Brook. And there are better bounds
I don't
now.
understand that symbol on the left. Can you say, I don't understand.
D squared over 4.
D squared over 4, and then you have plus O of D out to the side, okay. D squared over 2 would be squared over 4 plus O of D, okay. Thank you.
So basically, it grows, the maximum possible number of cusps grows quadratically with d, and the coefficient classical was known to be between 1/4 and 1/2. The best bounds are between 0.31, I think, d squared and 0.29 d squared. Okay? So these are not 0.31. It's some fancy number which I cannot write down, but this is. So of course you would bet that in between this there is 0.3. Okay? And I would like to argue that this is also a question about differentials on Riemann surfaces. Okay?
Maybe it's pi over 10, depends on the next digit.
It is 0 over.
Is that OD and OD squared?
Okay, so it's pi over 10.
Yeah. So anyway, so I can have we have a complete description posted on the archive here. Let me say why this relates to this. So let x, y be the non-homogeneous coordinates on CP2. Right? So x and y on CP2. So dx and dy are then meromorphic one-forms on x, such that for any loop gamma in x, the integral of this loop of dx or dy is 0, and they are common 0. And common zeros of dx dy are the cusps. Okay? So this is a question really about a curve. Again, it's a plane curve with a pair of differentials with 0 periods, with some prescribed periods, and about their common zeros. So this is also a question about this. And you can try to study it in these guys. And this is what we've been doing with Igor Pitcher and Kai Norton, who was my prior student here. And I would love to write the results we get here, but there is a problem that if I make a single mistake in some tool, somebody will come up to me and say that I have just obtained a contradiction in mathematics. And let me say where the contradiction from mathematics will come from. So you see, if I have an arbitrary complex surface, I can try to map it to CP2 and represent it as a branched cover of CP2. And if I do it in a sufficiently general way, it will branch over a curve, the only singularities of which will be nodes and cusps. You can prove this by some local deformations that if you perturb a branch cover, the branch curve will only have nodes and cusps. And if I have a bound here of this sort, I can get some bound for the Chern classes C1 and C2 of this surface. And if I write the wrong number here, which I did at some talk some years ago in the past, then you will contradict Bogomolov-Miyayoka-Yau inequality immediately. So this is really not some obscure question. So if you can prove something good here, you have proven some version of Bogomolov-Miyayoka-Yau inequality for some class of surfaces. So this is not such an isolated question. This is called, by the way, Chiesini question. It goes back some long number of years. There are works and so on.
How close to the Miyayoka-Yau line are these? The examples you're coming up with as branch covers are very close to the Miyayoka-Yau line?
I'm not saying anything about branch covers. I'm just trying to say that if I could prove, if I write here that the maximum number of cusps is less than 0.3 d squared plus the correct linear term plus the wrong linear term, and then I will have proven Bogomolov-Miyayoka-Yau inequality for an arbitrary surface, not necessarily of general type, which is not a good idea because it fails. I'm not going back from a curve to an actual example is a separate issue. But I'm trying to say that if I write 0.3 d squared plus I forget what's the coefficient of d, this would be definitely wrong. So this is very close. And it relates to surface classification in some ways that you may not have imagined. Okay? So this was by way of introduction. So this are two setups where I'd like to work. Now I should tell you what the approach is. Approach is by degeneration. So you want to answer, does a general, maybe very general, depending on how you think about it, xw such that blah 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 satisfy some other blah blah blah. So we are trying to ask questions. If you have a pair XW such that the multiplicities of zeros and poles are prescribed, or such that the periods are prescribed, or such that some other favorite condition you may have, does it satisfy some other property? And the approach to doing this is you check whether this holds for the degenerations.
How do you think of a meromorphic thing on the surface with curved nodes?
So that's exactly what I have the next 40 minutes to describe this for you.
Oh.
Okay? So the
I mean, what's
approach,
the definition?
that's why I have the next 10 minutes. Take a while. Okay? So approach is, so answer by degenerating xw to something singular, arguing that a singular thing satisfies whatever it is that you wanted it to satisfy, and then say in a generic, and then arguing openness of condition. Okay? This is how you approach such things in more in algebraic geometry. And doing this came
Like
about.
an inequality or something?
Huh?
Not-
No, so
not
I'm
equality.
being very vague. I'm not saying precisely what I want. So suppose you want to know whether a general pair consisting of a Riemann surface on the one form, such that the multiplicities of zeros and poles satisfy some condition that I don't know what it is. Suppose this condition is open, including going to the boundary. Then I need to demonstrate one point where this is satisfied, then a generic point will satisfy it. Demonstrating one point is hopeless, because if you ask me to write down a general curve of genus 27 for you on the blackboard, there is no way. I can write down equations of curves of genus 27 on the blackboard, but most likely the fact that I can write them will mean they're not generic, because they have some special properties that will allow me to write them. If you ask me to write a general curve of genus 27, I don't have a chance. However, it may be that I write down a degeneration of a curve of genus 27 that I can handle somehow combinatorially. Okay, and this is the approach. And the development of the modular theory of curves and various progress on classical Bernoulli-like questions and something like that came from degeneration. Not only, but this was one very powerful. Okay, so this was the introduction. Now I'd like to describe what degenerations look like. And first I will tell/remind you what the degenerations of Riemann surfaces look like. The degenerations of X. Okay? So X is a Riemann surface. So I'll write that it sits in MG. So this is moduli space stack of Riemann surfaces of genus G. Okay? And you would like to compactify the space. This space is not compact. And you embed it in MG bar, which is a Deligne-Mumford compactification. And the fact that you have a compactification, which is a nice algebraic object, is a very deep and amazing theorem that has made all of these things possible, and it is due to Deligne-Mumford. And I won't prove this theorem for you, I won't even try, but I'll tell you what objects here look like. So objects here are nodal curves with some stability condition that I'd like to sweep under the rug for the purposes of this talk, because that's not the interesting stuff. So what does a nodal curve look like? So I'll start drawing pictures. So here is a genus 2 curve. Okay? So this is a Riemann surface of genus 2. We all know what it looks like.
It doesn't look like that.
Well, it depends what shape you prefer. So, I draw this. Okay? This is what a differential geometry would draw. This is what an algebraic geometry would draw.
Sounds good.
Oh, sorry.
Thank you.
This is actually a very comfortable remark, because I was going to make that similar remark. So this is what an algebraic geometer. So this is a curve, smooth curve of genus 2. So I just think of it as a curve. I'm drawing sort of a complex picture. It's a one-dimensional object. And since I cannot draw on a one-dimensional object any holes, I write the 2 next to it to remind myself they're there. Of course, this is more comfortable. This is much more useful because I'd now like to draw nodal Riemann surfaces and explain what these are. Okay. So all my pictures will be in genus 2 because I want it to be visible. Whatever questions you want to ask in genus 2 are completely trivial and not interesting. You should not be studying them in genus 2. I will still pretend I'm solving them in genus 2 because that will allow me to explain the techniques. But for doing anything in genus 2, you don't need anything. I mean, every Riemann surface of genus 2 is understood so well you can do pretty much everything you want to do. So there are degenerations. So how do you degenerate things? You degenerate by pinching curves. So degenerations are the nodal genus 2 Riemann surfaces. And they come in sort of two, the simplest degenerations come in 2 kinds. This is one kind, and this is the other kind. Oops, thank you, Dennis. Okay, so these are 2 kinds of degenerations. These are very confusing pictures. If you have never seen such pictures before, think about what happens locally near this point. So locally near this point, it looks to you like 2 things are touching in 3 space. That's the wrong picture. This locally should look like xy is 0 in C2. So these are 2 complex things intersecting transversely in the complex 2 space, which of course I cannot draw. So I draw that, but they don't touch. They don't have a common tangent space. So they just intersect transversely, know nothing about each other, they just touch. Okay? So this is how you draw them if you're a differential geometer. This is how you draw them if you're an algebraic geometer. 1, 1. Okay? So 2 curves, each of genus 1, intersects in 1 point. I would like to argue this picture is readable. You know what I mean. 2 smooth curves of genus 1 intersect in 1 point. Here, what should I draw? It's sort of 1 curve that intersects itself in 1 point. And I should put a number on it to remind me of how many holes there are still in this smooth thing, right? There is still 1 hole that I didn't draw, so I should draw it. Okay? And then you can also have an object which is called dual graph, which I'd like to introduce now.
What do you do with those ends
What ends?
of that drawing?
Oh, they go off to infinity. So this is a curve that just continues. And just my blackboard is not infinite, and my time is very short, so I don't draw infinite curves. So this goes off to infinity. You think these are 2, you mentally think they're like lines or
You
curves.
think it is in the projective plane, for example? Or?
You don't want to think of them in the projective plane because not any Riemann surface can be embedded smoothly in CP2, so you don't want to do that. But you think this is a smooth curve, abstractly justified. The real reason, I think, is not even this. So I'll draw dual graphs. And if you start working with degenerations, you don't draw these pictures. I will keep drawing these pictures for you. I'll stop drawing this in a second because for more complicated degenerations, I'll suffer. Well, this is how you really do this. So this you draw like that. And this you draw like that. Okay? So let me explain what this means. So this is a dual, whatever, cell complex or something. So a vertex here corresponds to an irreducible component, or component of the curve, and edge corresponds to a node. And of course the numbers are the same numbers. So here I have 1 component of genus 1, another component of genus 1, and they're connected by 1 node, so 1 edge. Here I have 1 component which has its normalization technically, has genus 1, and it has 1 node from itself to itself. So the edge goes from itself to itself. So the edge connects 2 components that contains the pre-images of the node form. But I don't want to spell all this out. Okay? This is what degenerations of X look like, and you can keep going. So you can degenerate as much as you want, you get more complicated pictures. I'll draw some more complicated pictures in a few minutes, so we'll have more to chew on. And this is what we'd like to study. And so the question is degenerations of differentials. So I hope you have all memorized and will always remember all of my coordinates. Okay. So that's all. So I have described for you what points of the Deligne-Mumford compactification look like. That's all. What I'd like to do now is I'd like to try to start describing the degenerations of Riemann surface together with the differential. And I have to tell Dennis and all of you what the degeneration of a differential looks like. But before I do that, I wanted to do a sample problem. I wanted to pose, not to solve a sample problem. So I'll do it here and I'll try to keep it. Is this still visible on the other side of the room? Borderline? Enrico?
Fine.
Julia? Borderline. So here. Okay, sample problem. Let me introduce notation. Notation. I will only talk from now on about holomorphic differentials because I don't have much time. It conveys all the important things actually. We have the results for meromorphic, but ignore them. So omega mg is a moduli of pairs consisting of x and omega, and this is a holomorphic one form on x. Okay, so just holomorphic one form. That's notation. Next piece of notation will be omega mg. Let me 2, 1, 2. So this is moduli space of triples x, z, omega. So x is a Riemann surface of genus 2. Z is a point on x. Omega is a holomorphic one form such that omega has one double zero, no other zeros, and this double zero is at z. So if I have a holomorphic one form on the Riemann surface of genus G by Riemann-Roch degree count, canonical, bundle, class, formula, whatever you call it, it has 2G minus 2 zeros. So in genus 2, a holomorphic one form has 2 zeros. And I'm requiring them to actually be a double zero. That's the simplest condition you can impose. And I'm requiring this double zero to be not somewhere, but at this point z.
Does a 1 mean you have 1 point z?
So 1 means that I have one mark. So this notation, I will write the generality. So this is to say that I have a genus 2 Riemann surface, one marked point. The differential, there is a differential, and the differential is supposed to have one double zero. So I could write longer list, and I will when I try to state what the theorem looks like as that.
And the zero has to be as a mark.
The zero has to be as a marked point.
Physical.
Yeah, so I mean, I'm writing this double zero is at z. Otherwise, it's somehow silly. There is a marked point one place and a differential elsewhere, and I don't care. So the question is, what is a closure, the closure of this?
Is there a good closure of this?
Yeah, well, I need to say closure where, which I won't say now. I will say in a second. But I wanted to tell you what the examples that you should keep in mind are, and I'll write them here. Nikita, is this easy?
Why do you have to say closure where?
I haven't told you yet. I'll tell you in a
Well,
second.
why do you have to? You could just say it's a compact thing.
Well, this is not compact because
no, after you
after I
get it.
close, well, but then I can have a one-point compactification. That's not what I'm looking for. So I will want a closure in some space that sits over the Deligne-Mumford space. So I know my Riemann surface should degenerate in the Deligne-Mumford way. Okay? And I'd like to draw now 3 examples of degenerations where I'd like to ask ourselves, given what happens. And again, I warn you that, algebraic geometers in the audience, presumably if you ask them this question about this particular case, in the next 5 minutes they'll tell you the answer. with some machinery, not using anything of what I say, but I will demonstrate the results in this case. So, examples. So there will be 3 examples that I'd like to draw of what can happen. So how does this degenerate? So I have a Riemann surface of genus 2. We know how such things degenerate. And then I'm supposed to draw a point somewhere on it. Well, I just put a point somewhere. And the point really should not be a node. Okay, so it should sit on one of the components. That's how you delimorphic compactify moduli space of curves together with a point, with marked points. Okay. So the examples I'd like to consider, so the simplest is there are 3 possibilities. There are 3 kinds of nodal curves. So one is this. Okay? So this is a Riemann surface, a nodal Riemann surface of genus 2, 2 components. I've been drawing them like that, I'll draw them like that, and the marked point sits on one of the 2 components. Okay? So let's call this A. B is an example. I'll draw this picture first because it's easier for me to draw this picture, so then I have to think what it actually means. So it means I have 2 components, and sorry, this is 1, 1, and this is 1, and this is 1, and this is 0. This is stable if you're worried about stability, but we're not talking about such things here. Okay, so that's the corresponding smooth picture. So there is an elliptic curve, which is one thing, and the sphere attached at 2 points with 1 marked point. And there is case C. As you can see, drawing this picture gets much faster. And there's only one way to put generate here because it needs to be stable. Never mind that remark. Okay. So 2 elliptic curves with a sphere between them with 1 marked point.
So, Sam, how can you get a closure in this case?
A closure.
If you move the point to the node, you're suddenly forbidden, right?
So you're asking exactly the question why the delimorphic compactification is compact. So if I move this thing to the node, I can't, because this is a sphere with 3 marked points. It's rigidified by the action of the automorphism of M03. It doesn't move anymore. It's not allowed to move. Here, I can move this marked point to the node, and then I'll have to break out an extra component. I'll need to blow up. I'll end up here. So this case is a further degeneration of this case. It is not a degeneration of this case.
So is it so the 0 of your form counts for the stability condition?
Well, the marked point counts. So these are pictures here in MG2 bar. So these are pictures in M21 bars, right? These are loci of nodal curves, Riemann surface of genus 2 with 1 marked point. Okay? And the question should be, given such a Riemann surface with such a marked point, does it lie in the closure? If you wish, you take this locus and you just forget the differential. The differential, after all, is determined by its zeros up to scaling. So I can map this to M21, and I'll get the locus inside here. And you ask whether these things lie in the closure of this locus. Okay? This sounds very fancy. I'm asking something very simple. What is the closure of the locus of y express points of hyperelliptic genus 2 Riemann surfaces? At this point, you can take your pen and compute, and you will get the answers very quickly, but this is not what we're going to do. I'm taking an approach where I view this as part of a general picture. I'm going to try to answer this question for you without using the fact it's actually genus 2, which is to say my result will be for arbitrary genus, arbitrary collection of zeros and so on. Okay? So let me try to pose the question to which the answer will be eventually.
Sam?
Yes?
Is there a reason why you didn't draw the irreducible case?
Yeah, it's not so exciting. I mean, I can, but I wanted to make some pedagogical point at the end, which will be best made here. Okay? So these are the 3 cases where I'll be able to make my points. This is not an exhaustive case. Okay? So where do I close up? So I need to tell you finally, Dennis has been waiting on this for a long time, so I need to tell you what are the degenerations of a pair x omega. Okay? So I have this omega mg, So these are moduli of pairs x omega, where omega is a smooth one form. I can write it this way, I can write it this way, I can write it which way you want to write. It's a holomorphic one form. Of course, I can forget the one form and I get moduli of x, right? And this is a rank G vector bundle, because on each smooth Riemann surface of genus G, as you learn your introductory Riemann surfaces course, there is a G-dimensional, not in the one entity in the semester, but anyway. So you'll learn that there is a G-dimensional space of holomorphic one form. So this is a rank G vector bundle, called Hodge bundle.
For what?
Huh? Hodge bundle.
Okay.
Because this is a variation of Hodge structure. And I'd like to compactify this over mg bar. So I have this bundle. And this, of course, fits inside mg bar. And I would like to compactify the bundle. Okay? And I have to tell you what the objects are. And the answer is as follows. So an object here is x omega, where x is, of course, the same as here, as a nodal Riemann surface. And omega is a collection of meromorphic one forms on the components of x with at most simple poles in the nodes with opposite residues. So this is nothing new. This has been known in algebraic geometry since the construction of the Dean-Mumford space. This is a mouthful to swallow, so let me try to explain what this is in two simple examples in genus 2 that I drew here but have since erased. Okay, so here is this one example, and this is case A, in fact, right? So 1 and 1. So I would like to know what is the form in this case. So this is my x, and I have a form omega 1 here and the form omega 2 here. So this is a limit of holomorphic one forms on smooth Riemann surfaces. And what this description tells me is omega 1 has one simple pole. At this point, let's call it P. Okay? But of course, the residue theorem tells you that this does not quite happen. So this means omega 1 is in fact holomorphic. Of course, by the same argument, omega 2 is holomorphic. So in this case, the limit of holomorphic one forms gives me a holomorphic one form here and a holomorphic one form here, which is acceptable. And if you compute the dimension, this is genus 1, there is a one-dimensional space of forms here, a one-dimensional space of forms here. So I get a two-dimensional space of limits, which matches my claim that this is in fact a rank G bundle. This is not mine, Mumford certainly knew that. Okay? This actually goes further deep in history than Mumford. This is done well, it can be done by an easy local computation. So this is one possibility. The other possibility is, this. So remember, this corresponds to this Riemann surface. Okay? So this is an irreducible Riemann surface with one node. Here I have an omega. And this omega is a form on a genus 1 Riemann surface. If it were holomorphic, I would only get dimension 1. But here I have P, which has two preimages, P1 and P2. So P1 is sort of on this side, and P2 is on this side. And omega has residue, R at P1 and minus R at P2. So if I think of omega as a meromorphic one form on an elliptic curve, it has two simple poles with opposite residues. the dimension of such things is exactly 2, so this still works. Okay? I was hoping to explain this better, but it didn't work. I don't have time to explain this. Let's see what this means for our problems. So let me try
So the
to...
point is you get the right dimension.
I get the right dimension. This is not enough to prove that this is the right extension, but it is. The fact that the dimension is right, you do by an easy combinatorial argument, that's not a big deal. The fact that gives you a vector bundle extension of the Hodge bundle is a statement, which you can prove by local deformation theory, because you write this as locally as x, y is 0, then the form is dx over x, which is the same as minus dy over y, and you deform it, and it all works out literally in one page of computations, 5 lines of which I was hoping to show, but wouldn't work. Okay, yeah, Anu?
Is it the same thing as considering the form on the normalization, imposing like
No, I mean, so this is really a form on the normalization of components. I mean, slot. I tried to not say the word normalization, but it's a form on the normalization with poles. So I don't know what it means to have a form on a singular thing. So I normalize, I disconnect all the nodes. One of the many things I've done.
It can't be thought of as a suitable section of the dualizing sheaf?
It is. This is exactly the same as a smooth section of the dualizing sheaf, but saying this would require me saying. I mean, this is how to do. I try to tell you that the section. I mean, this is a sheaf. This is a vector bundle of sections of the dualizing sheaf. The dualizing sheaf extends. The sheaf section extends to the vector bundle. But I mean, I want very concrete things. Okay. So let me try with this understanding and go back to this wonderful example. So I want to know whether such a thing lies in the closure of this. And now I can tell you what the closure is. Well, no surprise, the closure happens here. Well, I didn't put the 1 here, but imagine I decorate this diagram with ends for the fact that there are just n marked points everywhere that play no role. They don't see, the form doesn't see them, nothing happens. You just put n marked points, no changes. So then, this is a subset of this, and I can take the closure. Okay? So I want to know whether such a nodal Riemann surface lies in this closure, which means I need to find out whether there exists a form, omega 1 and omega 2 here, which is a limit of forms that have second order 0 here. Let us call it Poynter's constant. Okay? So omega 2, as we learned, is a holomorphic form on an elliptic curve, on a genus 1 Riemann surface. It must have a double pole, obviously, because this was a condition. So a holomorphic form on a genus 1 Riemann surface doesn't have, with a double 0, I'm sorry. Right? We are asking about the locus of Riemann surfaces together with a form that has a double 0 at this prescribed point. The limiting thing must have a double 0 at this point. But then it means that this omega 2 is identical to 0. Okay? Which means I have suddenly lost all information completely. And you can ask yourself if this is indeed a satisfactory answer. Meaning, does this mean that the position of this point plays no role anymore? What does this mean? How can I extract any useful information? Because if I want to say that an identical 0 form has a double 0 somewhere, that's meaningless. So I need to extract some information. If you look at this example here again omega has to be identical to 0. Because again, there can be no residues here. And the thing on the sphere now must have a 0, which is impossible. Okay? Here, this is a sphere, a Riemann sphere, and I'm asking for a form that has 2 simple poles on the double 0. That again does not work. So again, omega on this component has to be identical to 0. So it says that in all these cases, I have completely lost all control if I have just tried to take the closure in the space. Trying to take the limit thing tells me nothing. I get something identical to 0. Okay? So the way you do this in algebraic geometry is you try to do what I call limit linear series. And this is wonderful, and they have been wonderfully effective and well developed for Riemann surfaces of compact type, whatever this means, but not for general Riemann surfaces. Okay. But at this point, let me try to state the theorem, which I was hoping to give more motivation for, and which I'll then apply here. So it says the following: x z1 through zn omega, which is a point in omega mgn bar, lies in the closure of omega mgn m1 n. So what does this mean? This means x is a Riemann surface, z1 through zn are points, omega is a form, such that the divisor of omega is the sum of mi zi. All mi here, well, for the purposes of what I'm saying, should be greater than 0. So this is a holomorphic one form. I have labeled all zeros with multiplicities, and I want to know what is the closure here. So the statement will be that the point lies on the closure if and only if there exists eta, which is called a twisted differential, which is a collection of meromorphic one forms on irreducible components of x with only poles, with poles only at some nodes. And L, which is a level function, which goes from the set of irreducible components of x to, doesn't matter what you write, I'll write z, but you could write r, makes no difference. All that matters is the order it induces, such that, and then there will be a long list of conditions. Before I write the long list of conditions, let me say what this really is. What this A omega really is the following. If you have a degenerating family, something became identically 0. So you want to take out the vanishing order. So if your family was parameterized by t, you just divide this thing by some suitable power of t, so that the limit is no longer 0. And then this limit will start having poles at various places. And I'm just listing the conditions that such a limit will have. And once I list them, it is actually very easy to show that the conditions are necessary, which means that limits satisfy them. And that, if I were given a seminar talk, which I have done many times, and if I started without motivations and last time, I would have proven the necessity. That would not be hard. Sufficiency is completely different story. It's much harder. Okay, so conditions. So condition number, -1 is on top level components. Eta is equal to omega, and omega is identically 0 on components not of top level. Top level means the maximum of this function. Okay. Condition number 0 is for any point zi, the multiplicity at the point zi of eta is what it should be, precisely mi. Sorry. When I say twisted differential, it's the selection of non-zero. So the important thing is none of them are 0 anymore. My problem was they were identical to 0. So it has correct multiplicities. Second is for any node P with preimages P plus minus, the multiplicity of eta and P plus the multiplicity of eta and P minus is -2, which is to say they add up to the same as a simple pole would have added up, which is the case if you twist. Second, if this multiplicities are -1, then the residues third is if P plus lies on some component x plus, which is irreducible component of x, and P minus lies on some other x minus, then the multiplicity of P plus of eta is greater than or equal to -1 if and only if this component is larger than the other component. So I have ordered all the components by their sort of vanishing order. Now this is to say that the differential is bigger on bigger components. And for the residues of eta satisfy a bunch of many linear relations, which are known. These are called residue conditions. I have run out of time, so I won't state what they are, but they're explicitly known. Up to here,
That sort of say it's a cycle on the graph.
here, this?
Yeah.
No. This says that suitable version of Stokes' theorem is satisfied before degeneration. It does not have an interpretation. So this unknown, up to here, this is reasonably clear if you're thinking about twisted linear series from algebraic geometry. What is not clear is that A, you have such condition a priori, and B, that this is all you have. So the fact that you have such condition is not very hard. The fact that it's enough requires a proof, and which is why this paper is not 5 pages, but more like 55. Okay? Let me try to explain how this applies to the 3 examples at hand, and then we'll be done. And then, of course, I should say that this applies to much more generality for meromorphic differentials, for K differentials, and so on and so forth. So many other ones. So let me look at this example here. So I'm supposed to have a form eta 1 here and eta 2 here. Omega 2, as I described before, was identical to 0. Omega 1 is not identical to 0. Okay? And omega 1 is equal to eta 1 here. And then what is eta 2? Eta 2 is supposed to be a non-identically 0 form here, satisfying this whole bunch of things. So let's call, this point is called P plus, and on the other side it's called P minus. And the multiplicity of omega 1 and P plus is 0. This is an elliptic curve. I have a holomorphic 1 form, it has no zeros. So the multiplicity is 0. Okay? Which means, by this match and orders condition, means that the multiplicity at P minus of omega 2, of eta 2, this is the same as eta 1, is equal to minus 2. So this means if I look at this component, I have eta 2 on it, and the divisor of eta 2 is 2z minus 2p minus. Right? It has a double 0 at z and a double pole at p minus, and that's it. Well, that's your condition. If you know Abel's theorem, such a holomorphic differential exists if and only if 2z is equal to 2p minus under the additional law on the elliptic curve. Which is to say, if and only if these 2 points differ by a 2 torsion point on the elliptic curve. That's your answer. This is very easy. The residue condition is not used, this is not used, this is not used. So this is easy and was done well before us. Okay, here, again, omega 1 is non-zero, the same as eta 1. Omega 2 here is 0. Eta 2 must have a double pole and a double pole here. Right? And now you are asking for a meromorphic differential on the Riemann sphere on CP1 with 2 double poles and 1 double 0. Such a thing certainly exists, is unique up to scaling. So this means this locus is entirely contained in the closure of the locus I wanted to take. So any such curve is the limit of what you have. Okay? This case here, so I have eta 1, eta 3, omega 2, eta 2. These are non-zero. Okay? This is non-zero, so the order here is 0, so the order on the other side, the multiplicity of eta 2 here is -2, and the same here. So again, I have a Riemann sphere with 3 points. At 1 I have a double 0, at 2 I have double poles. This is again possible, except this condition here, which I didn't write down for you, says, condition 4 says, residue here is 0, and residue there is 0. Okay? I didn't write down the condition, but it basically says, take out the component of everything else, and wherever you connect to this one component, the sum of residues is 0. So the residue here is 0, and the residue here is 0. And now you ask yourself, if you have a CP1 and 3 points on it, you can as well decide that they are 0, 1, and the things. Does there exist a meromorphic differential with 1 double 0, 2 double poles with no residue? And the answer is no, it does not exist. So this does not exist. So this is disjoint, this locus is disjoint from the closure. Okay? So no such curve is a degeneration of the set of Weierstrass points on Riemann surfaces of genus. Okay? If I wrote down this condition fully, we will see the full answer. So that's it. Okay, sorry, I'm over.
Any questions?
So you were talking about this SL2R action that just happens in the story. So what's the relevance of
Well,
this?
the SL2R action happens, so this question is relevant in SL2R action. So the SL2R acts in this. The action of SL2R is on such locus because it preserves multiplicities of zeros. So this is a natural space for the action of SL2R. And you know from some considerations that go beyond the scope of this, that any orbit, that there are no closed orbits, that they must hit the boundary. So if you want to have some applications to dynamics, you would want to study orbits but by what the intersections with the boundary are. And then you should ask what the boundary is. And this tells you what the boundary is. I cannot give you a nice application yet because the applications that have been in dynamics for the generation arguments use much less. The paper is half a year old, so hopefully there'll be some dynamics applications. But this space is the total space on which the right-middle dynamical system acts. So we should study it.
The SL2 action is natural with respect to these closure operations. That's implied by what you're talking about. I mean, it extends to the closure.
No, and there are issues with that.
Huh?
No, there are issues.
There are issues?
No, there are issues. It's not true that there is a natural SL2R action of the closure. This is complicated. There are very technical and deep issues there. So if I try to extend the SL2R action to the space of this twisted differential theta, that's a big mess. And fully understanding this will help, but not necessary. But already knowing that if you have an orbit that goes somewhere, the orbit has a limit point that looks like this, is already quite a bit of information. So from knowing much less than that, from discarding everything except the components where the differential is non-zero, Mirza-Hani and Wright got some non-existence result for some technical orbits. So this is the setup in which technical dynamics works.
You also mentioned cusps.
Yes.
They didn't appear.
They didn't appear because my hopes for the speed did what I always tell the speakers who come here to this department. That our talks go much slower than you would think, and I forget this myself. So the cusps are the case where you prescribe the periods, right? And then you can try to study a similar story. If I prescribe the periods to be 0, in fact real, in fact the A periods to be 0, what are the limits of such things? And then again there will be a twisted differential of this sort that satisfies some conditions.
But it wouldn't be over this Deligny-Montfort.
It will be over the Deligny-Montfort, but there is no smoothness. I mean, notice I never said we have a nice complexification of this thing. I have computed the closure is somewhere. This closure is not smooth, its singularities are not Cohen-Macaulay, you can get arbitrary toroidal singularities, it's a mess. Constructing a good complexification is a different thing. For applications with dynamics, maybe that's not so useful. For people who want to compute the classes of the strata, which are important in some symplectic field theories, you want a complexification on which the intersection theory is well defined. That has not been done.
So
So the new number can come back to the beginning and then assume in terms of hyperbolic metrics.
Yes.
And be there to make it similar.
Oh, well, here, I mean, for this problem, this comes from flat surfaces, so I should understand this in terms of flat geometry. So this means I have x together with omega. I locally think of omega as dz, which means I will glue my Riemann surface out of flat pieces with cone angles. So I can understand this in terms of flat geometry.
So it's the same thing?
But you get the same answer. So our paper contains two proofs. One proof is by complex analytic plumbing. One proof is by flat geometry. The equivalent establishes the equivalence line by line is not so trivial. I chose not to say the word flat surface in this audience because I'm not sure that it has been said many times in Stony Brook, so I could take more time. You should not think of hyperbolic geometry when you're doing this, because you have one specific one form with specific zeros and poles. So you should think of this as a flat metric with cone singularities.
But the cone angle can be big.
The cone angle is fixed. And this is the order, the cone angle is the order of the zero cone. So then your Riemann surface splits, and then where it splits, you're gluing a zero on one side and the pole on the other side, which have equal cone angles at different sides.
Okay, let's thank the speaker.